So this is a collaborative project between two labs. So Vince, Julia, and I will be giving this presentation together today. So what is a split belt treadmill and why do we care about it? So this is a split belt treadmill. As you can see, it has two individual belts and each belt can move at its own velocity, and people will typically walk with one leg on each belt. So this means this is a novel motor learning task, and that makes it really interesting for us to study it. And not only that, because it's a walking task, it's used widely in gait rehab for people with gait impairments, such as stroke patients. So this provides us this complete paradigm, which we can use not only to understand like learning behavior of a healthy nervous system, but we can directly use it in the same task for people who actually need this knowledge. So this specific project I'm going to talk about is actually a branch off of another great collaboration that started right here at Dynamic Walking 2 years ago. It's between James Finley and Natalia Sanchez and Max and I. And if you remember, Natalia gave a talk about the results of our second project yesterday. But I'm going to do a quick recap of the results of our first project, where we found that if people can walk with the right gait, they can actually harness energy from a split belt treadmill. So this video shows that right gait. So here you can see that the left belt further away from you is the fast one, and this is the slow belt. And you'll see that when she lands on the fast belt, she lands with the left leg making a large contact angle. And when she lands on the slow belt, she lands really nearly vertically on the slow belt. And you should remember the specific gait because this is going to come up multiple times today. And it is this gait that lets her harness the energy from the split belt treadmill. Yeah, so we were really excited with these results. And at the end of last year, Max and I also went to this other conference where Steve Collins was present. And Max told him about our results. The next day, he comes to us all excited and he says, I couldn't sleep last night. You have to see this. So this slide that you're going to see is what Steve did during his sleepless night. So I told you, yeah, people can harness energy from a belt speed difference. But what about a passive cart? Like if I were to put a passive cart on two belts that are moving backwards, you would typically expect the cart to also move backwards, right? But if this cart could also harness energy from the belt speed difference, maybe you can make it stay at one place on the treadmill, which we will call station keeping. And if it can harness enough energy, maybe it can actually move forwards and even upwards. So the cart I'm talking about right now is the ideal cart shown here. So this belt is the fast belt, the bottom is the slow belt, and you see that the cart is placed such that one wheel is on one belt and the two wheels are connected by one axle. And also, the two wheels of these carts don't have equal radii. In fact, the wheel with the larger radius is on the faster belt. So this is an ideal simplified cart, but it can still be a little confusing to understand how this works. So what helped us with intuition was to think of this as a water wheel. So here, if you imagine the water moving downstream, and it rotates this water wheel clockwise, and then the water wheel can rotate this wheel also clockwise, but this is on overground, which can then move the system upstream. And so that is similar to what our cart basically does on the two belts. But in our case, the fast belt acts like the water. And what's neat about our ideal cart is that you can define the velocity of this cart simply by using the two belt speeds and the two wheel radii. So in fact, by choosing the radii of the wheel, ratio of this radii to be equal to the ratio of the belt speeds, you can get the cart to station keep. And by making this ratio less than the belt speed ratio, the cart can move forwards maybe. So essentially what I'm saying is that we can decide how much energy this cart can harness from a given belt speed ratio by choosing the ratio of this wheel radii. And if you think about it, this is very roughly similar to what the mechanisms people can have available when they are trying to harness energy from a given belt speed ratio. But of course, this is all ideal cart, and reality is not ideal. So Vince is now going to talk to us about how an actual cart can harness energy from a belt speed ratio.
Yep, so here you can see the mechanical prototype to validate those equations. So it's super simple. In the front, we have a rudder that interfaces between the two halves of the treadmill in order to keep the cart steering straight. We also have two free spinning front wheels in order to prevent the cart from tilting left and right. In the back is where we have the two unequal wheel radii that Surabhi was talking about, and it is connected by a one-to-one gear train. And here you can see in the second inset that each wheel is on each belt. So when we place this device on a split belt with both belts going at the same speed, this is called tied belts, it moves backwards at the speed of the belts, which is something you'd expect. However, if we move one of the belts backwards even faster, it moves forwards. I'm going to play it again so you can applaud if you want. Oh, yeah. And actually, with the same belt speed setup, it will actually move up a 6% grade. Thank you, thank you, thank you. So we thought, wow, this is super cool. Let's try to bring it to the masses with a non-playing video. No. There we go. So we built a Lego version. It's super simple. In this case, we have wheels of the same radii, so instead we use a gear train ratio to achieve the wheel ratio. And so we tested this Lego cart with a similar belt speed setup, and you can see that it moves forward on a backward treadmill with different belt speeds. So if you want to try this at home, all you'll need is this Lego kit and the $100,000 treadmill.
So the concept of harnessing energy from the different environments worked really well with the cart, so we wanted to extend that back to walking. The simplest model we could think of as a starting point was the rimless wheel, but we modified it to have alternating leg contacts on the fast and slow belts, and we also have alternating spacing between the spokes. In simulation, we can find solutions where this wheel is able to roll steadily on a split belt treadmill, unlike a standard rimless wheel, which slows down with each collision. So to gain more intuition into how this works, we're going to look at the special case where one of the transitions happens with no spacing between the legs. And during this collision, the velocity before and after the collision is the same, regardless of the difference in belt speeds, as long as we consider it in the same reference frame. And during the transition onto the fast belt, which happens at a wider angle, we'll actually see that the treadmill is able to inject energy into the system. So before the collision, we start out with some initial velocity in the slow belt reference frame, but because the collision is going to happen onto the fast belt, we want to transfer that velocity into the fast belt reference frame before performing the collision equations. During the collision, just like a standard rimless wheel, we see the impulse going in the direction of the fast belt leg, and the new velocity direction is defined to be perpendicular, which gives us our post-collision velocity. We can see that the post-collision velocity is lower in magnitude than before the collision, which is what we'd expect. But when we transfer it back to the slow belt reference frame, we see that it's actually possible for the post-collision velocity to be equal in magnitude to the pre-collision velocity, or even larger in magnitude as we up the treadmill belt speed difference. So because all of the analysis is done in the slow belt reference frame, there is a small effective energy loss during the single stance phase on the fast belt. But the key thing to understand about what enables the wheel to roll forward is that enough energy can be injected during the transition onto the fast belt to compensate for any losses during the collision onto the slow belt.
Okay, so a rimless wheel is pretty close to walking, but it doesn't capture all the features of it. And so Max wanted to bring us as close to walking as possible, and so this is a dynamic walker right now. So this walker has 2 point feet. It has 2 rigid legs that have mass. It has a point mass body. And the 2 legs are connected by a hip spring whose equilibrium position can be tuned for. And the 2 legs can apply push-off forces impulsively when they're trailing. And this walker is always on level ground, but it's on split belt treadmill, and the red and so this red and blue tracks represent the 2 belts. And so this walker tries to solve for a stable stride cycle, and it does so by trying to minimize the push-off impulses that it has to apply. So this is what the walker does when the 2 belt speeds are equal. Looks like a symmetric normal walking gait as expected. And the solution that it finds is such that the push-off forces applied by both the trailing legs in one stride are equal. And also this hip spring equilibrium position that it finds is 0, and that explains this symmetric walking gait. Now, we keep everything constant, the same walker, and just make the red belt speed 50% faster. And this is what the walker does. So this is now on a split belt treadmill. The two belt speeds are different, and this is the fast belt. And the very cool thing about this is that this is completely passive. There is no push-off forces being applied. And not just that, the hip spring equilibrium position that it solves for is such that the red leg, which is on the fast belt, lands at a large angle to the belt, and the blue leg, which is on the slow belt, lands exactly vertically. And now if you remember, this is quite similar to what both the person did and the rimless wheel did to harness energy from the belt speed differences. Will this play? So those are our results, but we'd like to acknowledge that lots of people have done very similar work to this. And in fact, this figure that I used earlier is from Andy's paper from 40 years ago, which is still in revision. And it is also actually a paper about sailing. So this is just to show that this concept. Oh, okay. So that just means this. So again, my point is that this concept has been repeatedly presented in different systems and different media. So this is a very general thing. So yeah, and all of these people are working on similar concepts too. And thank you. So we can take any questions now.
Okay, question. All right, start from here again.
Alex from Xbox. Your principle requires that you have a mechanism which prevents the torquing, the rotation, right?
Yes.
Yeah. So,
Which like all of them, or pretty much? He's asking if any of these mechanisms require mechanism to prevent yaw, I think. Is that correct? Yeah.
So did you measure the amount of torque on the yaw axis for your different scenarios?
So this is the only actual part. Everything else is a model.
Yeah. Okay. Sure.
Yeah.
But here, do you have an understanding on how high the yaw torque is?
We didn't measure it, but it's definitely non-zero.
Yeah, we do see that you need a higher belt speed difference than the ideal cart equations predict in order to achieve the motion in reality.
Like in all the prototypes that we did, like without preventing the yaw, it was just done. So yeah, definitely we need something to prevent the yaw.
I'm sorry. Okay.
Just, I don't know if you appreciated this or not before, but something that people find unintuitive about these machines is that if you turned it around, it could walk in the same direction as the belts are going, faster than the fastest belt. So it goes faster than, so it goes with the belts, but faster than the faster belt, the same design.
So I think that's what this actually says. It's if you actually flip this ratio, if you make this greater than this, it would go with the belts faster. But I guess we didn't do that because then it just looks, you can't really tell if it's just slipping with the belts unless you can actually picture or like photograph the rolling and show that it's going faster. But yeah, that would be neat.
All right, question there.
Yeah, super cool stuff. So I have tried to get an intuition about the two rimless wheel model, and what I always struggle with, if you could go to that slide where you show the bottle. Yeah, keep going. There we go. Yeah. So you have V plus SR, which can, in principle, have higher magnitude in terms of velocity, but it's essentially going in the wrong direction, right? So the increase in momentum isn't going forward. It's basically being redirected either up or backwards. And so I'm just curious, what is the mechanism that sort of redirects that momentum from going with the belt to forward? Because that seems to me to be one of the main issues here.
I think it's that, like, because the point on the belt, there's enough friction, or in theory, like, it's attached to the belt is able to help because like we're looking at VSR in the slow belt reference frame, but at that point, the leg is actually moving on the fast belt. And so the way that the velocity as viewed in the slow belt reference frame is going to change over the course of that single stance phase is going to look a little bit different than if we were just doing that rotation in the reference frame of the belt that it's on.
Okay, we'll talk.
All right. Is it any more questions? Okay, there you go.
In your last video,
Last.
like the very last one where you have the meter model on the fast belt, yeah. At any point during the gait cycle, does the leg on the slow belt ever go in front of the fast leg?
Not in this solution. Never. That's what Max is saying.
It can, but it's not the ideal, it's not the optimal solution.
So it's optimizing to minimize push off. So I guess when it does go, when the left leg, slower leg does go forward, it's no longer minimizing push
Can
off.
you do the walk?
Good. Good. Good.
I can do the walk. Let's all do the walk.
Sorry. So it's kind of what it's doing, but it's not going forward. It's the left.
So you don't think that there's any way to do the same thing but have it look like, I guess, closer to walking where one leg is going in front of the other?
So the cool thing was, it is very close to how people walk on a split belt treadmill. So that was the video. So on a split belt treadmill, when they can harness energy from the treadmill belts, they're actually walking with the leg on the fast belt going on ahead, and the leg on the slope belt is almost vertical. Not exactly, because I guess it's a little more awkward for the two person, but they do something very similar to what the belt does.
So even humans aren't like walking normally?
Well, this is better than normal because they can actually get energy from it. It's cheaper for them. If they walk normally, and I'm assuming you mean symmetric gait when you say normally,
Yes.
it's more expensive for them to do that. So it's better for them to do this than.
Peter has
Okay.
a question.
Oh, Peter? Oh, okay,
Yeah, sorry.
one more.
Peter Adamczyk, University of Wisconsin. Your cart, you said, veered off to one side or the other without a stabilizing yaw torque, right? Which way did it veer?
I believe it veers towards the fast belt.
So I think you should investigate from your split belt walking whether there's a righting torque under the legs of the person who doesn't have an external torque actuator on them. Have you looked at that at all?
Oh, well, we haven't measured talks from actual walking people. I guess. Sorry. How do you? So what do you mean by from force plates? You mean?
Yep.
No, we've not done that. We
Come to
could do
think
that.
about it, because
Yeah.
you have a
Yeah.
new prediction now
Yeah.
that they should have to do that.
No, can I make a comment on that?
Yes.
Sure.
The forward impulse and backward impulse match. And you're getting, I think, only backward impulse from the one belt and only forward from the other. And that's, okay, that's what you're trying to balance.
Yeah.
So you're going to get an impulse in the yaw direction. So actually so Alex's point, I think, exactly, is very well taken. Actually making the
Physical version of the walk.
version might be
Yeah.
a little trickier than we
Right.
were thinking.
And also tricky for people.
And tricky for people.
Right.
Question back. Is there
All right.
nothing in the?
I think this is really interesting work. I encourage offline or more discussion. Thank you again. That's